Today we're looking at projectile motion. Just to recap free body diagrams from last time. Okay, make sure your diagram is emphasized here. Okay, what I mean by that is do not spend masses of time on free body diagrams or making detailed drawings of the athletes, etc. That's not important. Okay, make sure you're focused on the forces acted upon what the question is asking of you. So if the example here was of the layup shot or the shot, free shot in basketball, okay, you need to emphasize these forces here and make sure your arrows are proportional. Okay, what I mean by that is you don't want a force going off your page or the arrow that's too small. Okay, it has to be in line with the action of force, so i.e. the point in line with the point of contact and which direction the ball was going in. You can include an absolute angle which is in respect to the horizon, so theta here, so the angle between the line of action, the direction of the ball, and the direction of the horizon, so it gives an indicator to the reader where the ball was going. Okay, so make sure you take your time on these. These are very easy marks, like I said in the last video, okay, but make sure you double check your answer to ensure you've got everything that the question is asking of you. Today we're going to look at the effect of release velocity, height and angle on projectile distance. We're going to look at the 4 types of spin, and we're going to sketch out how the Magnus effect causes spin. So the angle, release, velocity and height of the projectile upon release are all very important, and then we need to understand in real world sporting contexts why these are important. So if the height of the release and the landing height are the same, for example, a flat hole in golf or football long pass, okay, we need to understand how the release angle impacts this. We need to understand how the release height, if it's greater than the landing, would be impacted. For example, a discus or a shot put or javelin, any of those kinds of throwing activities, or whether the release height is less than the landing height. So a bunker shot in golf where you're effectively below the ground. So for each different scenario, okay, we need to have a different release angle. Okay, so if you need to understand this in more detail, please pause the video. But if we are looking at a release height and landing height which is lower, for example, if we have a diving block here, we could have a swimmer that's diving into the pool for the beginning of the race. I've left some examples below, so if you want to try them out and to see which category they come under, then please do. So velocity of release, so the one that came to mind was Jonathan Edwards, the fastest man at 2000 Olympics. He was the fastest man in his run up to the triple jump. Okay, very interesting, so please have a look at this on YouTube and do your research. Very interesting. Athletes work hard to increase the velocity on the run up, long jump, angular velocity of the hammer. Okay, so velocity is very important. So coaches have known this for a long time, and I'm going to go over the science of that in just a moment and the explanations. The greater velocity takeoff, okay, the greater the distance. Height of release, so if let's go for example of 2 shot putters of identical release angles and strength, the person that's going to be taller will more likely throw the shot put even further, okay, than the one that's shorter. For example, if you throw a frisbee along the park on flat ground, it will go a set distance, maybe 60-70 meters. However, if you throw it off the edge of a mountain, okay, that distance, the actual or displacement the frisbee has been thrown would be a lot greater because you're at such a greater height. Okay, so I use the equation below in order to help me create the following Excel spreadsheet. So I looked at different parameters of velocity, release angle, and release height. I gave 14 meters per second for the standard velocity, 35 the angle in degrees, and height of 2 meters. Okay. And obviously I changed the parameters as I went along. The last one here, I looked at 50 degrees to 30, so a massive change of 20 degrees, see what would happen. And to be fair, only a meter of distance, horizontal range has been increased. But as you can tell, the greatest contributor to horizontal range was velocity. Okay, why is this important? Coaches particularly, they need the athletes to increase their velocity upon release, whether it be a javelin, discus, shot put, any of those kinds of events, or themselves a long jump, okay, or the goalkeeper kicking the ball, goal kick, whatever it may be. Okay, velocity is the most important. However, given that if your angle of release isn't excellent or accurate or on point, or however you want to describe it, okay, then obviously it's not as effective. So for example, for javelin, you throw it at 5 degrees compared to 30 degrees, that javelin will go straight into the ground, okay, and you will not gain a very large distance. However, if you were to throw the javelin at 70, 80 degrees, where it goes pointing upwards, so like that, if the direction of motion is to the left, you probably know from experience, from school, from club, athletics club, that the javelin will just go straight up in the air and straight down on its back. Okay, and if it points in the ground, it won't be the right end, so you won't score, you won't get a distance. It's an absolute nightmare. So the angle is obviously important, but without the distance, velocity, you would not gain horizontal distance. I hope this makes sense. Okay, please pause the video. Mathematically, if you're interested, why does velocity contribute the most? Okay, it's because it is squared, it's times itself within the range calculation here below. If you'd like to learn more about this detail in regards to how different projectiles travel different distances, we've given these velocity, angle and height parameters. Dr. Lynn Fawn at Brunel University has given some excellent research into this for a few years and can give you some excellent reading, particularly if you want to take this further at degree. Forces in flight. Okay, we need to understand that that object is experiencing weight and air resistance, okay, particularly on Earth, hence weight because it's mass and gravity. We tend to think of projectiles going in this nice parabolic upside down U flight. However, this is not always the case. For example, a football, okay, may land a bit shorter because they're heavier compared to surface to weight ratio, or a shuttlecock may go a lot further, okay, because they're very lightweight and they have a lot of drag, as you'll see in a moment. So when we're drawing free body diagrams as well, make sure that our arrows are pointing backwards, okay, not as such, because if you imagine the shot put is moving in this kind of flight path, okay, arrows need to be respectful to that. All right. Again, make sure your weight arrows and air resistance arrows are proportional. Otherwise, if the air resistance was equal to weight, there would be no forward motion. There would be no direction of motion going forwards. Okay, and it'll fall straight to the ground. So parallelograms are very helpful for identifying the resultant forces and how that object might react or behave in the air. So for example, a shuttlecock, like I said, it has a very minimal weight force coming down, whereas a high resistance or drag force. So realistically, it's going to stay in the air for a bit longer compared to a shot put. Okay, these are very handy for identifying the flight path of an object. So here we use Bernoulli principle. You may have heard this in engineering for things like aircraft wings or the actual biology, the wings of a bird. Okay, and it works as such. So we look first at the direction of motion. That is very key. A lot of students tend to ignore this and talk about it, and in actual fact get it in the wrong direction, and they explain it the wrong way around to the examiner and therefore don't get the marks. So make sure you analyze this. So this discus is going towards the right, it's going in the rightwards direction. These air particles here, okay, as they hit the top of the discus, they have a longer way to go. So therefore, if there's a longer way to travel, they create a low pressure system. Okay. However, these particles at the bottom, they smack into this bottom side of this discus. Okay, and have a lot less distance to get in order to get to here, respectively. So these particles need to get to the same place at the same time, because everything in life needs, they like to have equilibrium. Okay, so these particles want to get to the same place at the same time. So therefore, if they smack against this discus, okay, it's creating a high pressure system. Okay, that was what creates the lift. Okay, like I said, at equilibrium, these particles have a high pressure down here and a low pressure up here. That creates that lift. So the discus wants to stay in the air for a lot longer. Hence why I put increases flight time. So the distance this projectile has travelled has now gone a lot further due to its angle of attack. This angle here, respective to the object itself. Okay. However, if the direction of motion was the other direction, these two pressure systems would change. So there would be a high pressure at the top and low pressure at the bottom. So angle attack, why is it important? Okay, particularly, like I've said about the javelin earlier. Okay, so if the angle attack is so high, the javelin has a huge amount of air resistance if it's going. Okay, so the direction of motion is this way. Probably using my awful handwriting. If the air resistance is coming this way, I really should have put it here. Okay, then that javelin's going to hang in the air, and as we know, it's just going to fall to the ground. But on an F1 car, this actually acts as a mechanical advantage, because what we're doing is we're increasing the amount of drag, and that pushes the car down to the ground, and it creates more traction, and it increases the friction force for the tyres. So therefore, it can go around corners at much higher velocities. So this is why it is really, really important. You might think, well, we want the car to go as fast as it can. True, but over the course of laps and laps, this downforce actually increases the velocity of the car, because you can then add greater torque and power to the engine, etc., and it will go a lot faster, particularly around corners where they lose time. So the Magnus effect. So this is on a ball. Okay, so topspin has such an effect and backspin has an effect. This is very clear, particularly with table tennis. Okay, where you can, if you watch a match from the side, you can see how the spin affects not only the flight of the ball but the bounce. Okay, so with topspin, the ball will hit the table here and it'll ping up as such. However, with backspin, the ball may come down and then easily come off as such. And I'll explain that in the next slide. Hook is always to the left and the slice is always to the right. So if we have the direction of motion go to the right for this ball here, ping pong ball, the spin is going in a top spin. Like we said earlier, the faster therefore lower the pressure, it's going to be low pressure at the bottom here. And we have high pressure here at the top. Okay, so therefore the ball wants to go downwards, hence the Magnus effect of force. Okay, creating top spin. Here, pause the video and have a look at the diagram. The separation points are where the particles leave the ball and become eddy or wake points. Try and make sense of it yourself with the direction of motion. Resultant forces, I've covered this earlier, but please have a look at how topspin and backspin affect the resultant force. Okay, whether it wants to go back down to the ground or whether it wants to stay and hang in the air almost and have greater flight time. So the effects of spin on the bounce itself. So topspin, like I said, it's going to ping off very quickly. Okay, and it comes at you. So if we're in table tennis, it comes at you very quickly. However, backspin, okay, it wants to, because of the friction occurring, okay, so i.e. the friction is going in this direction, opposing motion, the ball wants to go upwards very quickly. This is very handy in sports such as golf, where the player wants to stick the ball almost onto the green and prevent it from rolling off, so it's an easy putt. Okay, I hope this makes sense to you. Please give it a like. Good luck with your revision. Any questions, please do your research, and if you need to, rewatch the video. Thank you and good luck.